My name is Cecilia Hageman. I'm relatively new to UOIT, and specifically the program here. I was hired permanently in 2013, but before that, for 22 years, I was a scientist at the Center of Forensic Sciences in Toronto. Has anybody heard of CFS, the Center of Forensic Sciences? Yep. Some people may have seen that. Sometimes they mention it on the news, and they usually mention it improperly. They'll say a body was found and it's being sent to the Center of Forensic Sciences. No, it's not. The body's being sent to the pathology unit. The Center of Forensic Sciences is all about scientific analyses of evidence found at crime scenes. So it doesn't do autopsies. We leave that for the doctors, of course. In an autopsy, for example, if a pathologist finds body fluid evidence that they need DNA analysis on, that's sent to Center of Forensic Sciences. If you are charged with driving while intoxicated and you have to give a blood and a urine sample, that's sent to the Center of Forensic Sciences. So again, anytime a scientific analysis is needed by any official investigative agency, police, fire marshal, coroner, that gets sent to CFS. I would imagine for those of you who want to do forensics, the CFS is probably where you want to work here in Ontario. It's a fabulous place to work. About over 200 technologists and scientists doing work in biology, chemistry, toxicology, firearms, documents, anything you can think of. So why am I here? Well, I think 22 years was enough. I was in court over 100 times giving expert testimony, and I thought this would be a great way to share some of that knowledge. So we have a staff here with extensive knowledge in lots of different areas of forensic science. My background was in DNA analysis and in bloodstain pattern analysis. So let's get the first one, DNA analysis. What kind of question can DNA analysis answer? Does anyone know? Why would we do DNA analysis on a crime scene sample? What's the big question that DNA can answer? Go ahead. Who? That's the question. It's who. And it's fabulous. This is different. Bloodstain pattern analysis tries to answer the question, what happened? What happened at the scene? And this is the kind of scene you might get to. It's a pretty rare event where you get to go to a scene where everything's nice and airy and it doesn't stink too badly. No, most of the scenes are really, really messy. Any idea what might have happened here beside the person being a sugar and caffeine addict, I think? I thought this was beer, but the last class pointed out to me this was all Coca-Cola. What do you see? What do you see here? Go ahead. Go ahead. Yep. Yep.
Clearly there was a struggle.
Why do you say there was a struggle?
Because everything is in mayhem.
It's a mayhem. Mind you, maybe they're just messy. You've seen the show Hoarders, right? Maybe they're just really, really messy. But look at this. Large pool of blood, so at least at some point here, somebody was bleeding out. Blood forms a pool. What do you think is happening here? Go ahead.
There was some kind of movement sloshing around blood?
Yeah, absolutely. So you have that kind of movement there. What do you think is happening here? Those little droplets of blood. Any ideas? Go ahead. It may be to the head. Maybe some kind of hit to the head causes blood to break up into small droplets and be dispersed about. You're going to see that. So, just a few things that you can see just from this overall shot. There was a very famous physicist, Ernest Rutherford. He was a New Zealander, but I think he taught at McGill over the around 1900 or thereabouts. And he said this, and I think it's quite true. He said that all science really comes down to physics. All science is physics, the rest is just stamp collecting. Which is a little bit harsh, But there's something to that, is that no matter what kind of science you do, you have to understand matter and motion. And what better way to start then with Sir Isaac Newton, who looked at the universe, looked at the world, and came up with 3 laws of motion. Those 3 laws of motion apply to everything that moves, be it planets, be it golf balls, be it droplets of blood. It's the same laws, so you have to understand them. There were a number of laws that he enumerated, but this is my favorite one because it really captures the essence of bloodstain pattern analysis. To every action, there is an opposite and equal reaction. If you do something to blood, blood does something back. And what it does back, the pattern that's formed, can tell you what actually happened. That is bloodstain pattern analysis. And it all comes down to Sir Isaac Newton. Blood is a liquid. It's going to behave, due to the laws of physics, like any other liquid. Blood that's hit, put in motion, those blood droplets are going to form spheres. Circular, 3-dimensional spheres. Why? Because that is the most energy economically stable shape. So when I look at blood droplets, to me it's no different than thinking about baseballs. You can throw a baseball up, it's going to come down in a parabola. You can throw a baseball down, it's going to go in a trajectory downward. You can just drop it, and it's going to fall down toward the center of the earth because that's how gravity works. Baseballs, golf balls, blood droplets, same laws, okay? So, when you go to a scene, one of the things you may see are circular stains. Small stains, sometimes maybe a centimeter across, sometimes smaller, sometimes larger. There's quite a bit you can tell just from that stain. Blood dropping onto cardboard, see that one more time, produces a circular stain. If that blood droplet, which is a sphere, hits a floor or a wall at 90 degrees, you will get a circular stain. You've just learned something. Every time you see that circular stain, you know the trajectory or the immediate trajectory of that sphere of blood. It hit at 90 degrees. So let's take this a little bit further. That shows a droplet on a floor. Let's try to imagine you saw this on a wall. You saw 90-degree circular stains on a wall. You know that they had to hit perpendicular, correct? The source of those spatter stains can be at that height, below that height, but not above that height. Think about a baseball. Think about a pitcher. You can throw that ball. It can go up and down. It can go down, but it can't go down and up. Anytime you see circular stains, circular spatter stains on a wall, you know that the source was at that level or below. Good, check that off. Let's see that droplet again falling from a higher height. Look at all that surface action happening. You see? Little droplets around that parent drop. The higher that passive drop of blood falls from, the more disruption around the edge of that stain. Those are called satellites and spines. Okay? And you might see a few on the scenes that we've made up for you there. So, circular stains. It's there. Let's make this more interesting. Blood droplets don't always hit at 90 degrees. What happens if they hit at a low angle? Let's go see. That's coming in at around 10 degrees. Look at that. What you see here is a directional stain. It's a directional spatter stain. Coming in at around 10 degrees. The pointed end is the travel direction. Some people call that the tail. I don't think that makes any sense. It's the pointed end is the direction of travel. So when you see this, you knew that that droplet came from above. It could not have come any other way. If you see a directional stain moving upwards, so the pointy end is up, your source of blood had to be below it. Key, absolutely key at crime scenes, because you want to know when somebody got kicked in the head or hit with the baseball bat, were they standing, were they sitting, or were they already on the floor? Because if they're already on the floor, the person with the baseball bat can really not realistically work with a self-defense argument, can he? So when we're at these scenes, we're always looking for these directional stains to tell us where the original impact occurred. So that's a directional stain. I want you to look for stains, passive drops that look a lot like this. So you're going to see some of these obvious directional stains, but in your scenes, you're going to see these ones that came in at 60, 50, and 40 degrees. These are kind of called bear claws. It's only because there's a nice smooth end and that there's a disrupted end. That disrupted end is the direction of travel. When you look at the floor patterns in your scenes, have a look for the direction of travel. That will tell you the direction that the person was walking when the droplets were formed, okay? Look for the bear claws. Blood, once it's out of your body, a lot of things can happen to it. It can be whipped around. We can see what are called cast-off patterns. But a lot of the time, what you're looking at crime scenes are what are called impact spatter patterns. It means there's blood that's out, sitting there. It receives some kind of blow. It's hit. It causes the blood to break up into smaller droplets and be dispersed about. Force equals mass times acceleration. Thank you, Isaac Newton, again. The greater the force, the smaller those blood droplets. What you see there are impact spatter patterns. So let's make one. There we go. Let's hit blood. Cool. You have blood, some of them moving faster than others, some smaller droplets, some larger ones. Look at that. Can you see the directional stains there? There and there. You can tell that they're going upwards and at an angle. See that one again? Here's a good hit. And there's your impact spatter. Coming out on both sides and toward us too, actually. There's your blood hitting at an angle. So if we saw this at a scene, but we didn't see this here, maybe it was somebody's head, right? We could look at these spatter patterns and go, you know what? I can tell it came from somewhere around here because I look at the direction. And I know it came from below it because they're upward moving. Let's have another look at the other one. I can't remember what it was. It's the hammer, right? That's a classic thing at a scene, hammers. A lot of smaller droplets there, eh? Seems to have hit a little bit harder. There we go. Don't need a lot of blood, eh? to produce those particular patterns. At the crime scenes, you spend a lot of time looking at these impact spatter patterns to try to determine where the person's head was, usually it's the person's head was, when they were hit. Hit with a hammer, hit with a fist, hit with a cricket bat, hit with a golf club, hit with a flashlight, you'll see it all. So these are 3 different spatter patterns that look kind of similar, aren't they? But they're actually all produced in very different ways. The first one is from a bullet going through a bloody sponge. Lots of really small little spatters there. The one on the right is from an impact, but not a gun. It was simply a baseball bat, okay? The one in the middle kind of looks like both. Came out of somebody's bloody nose. Let's have a look. When blood comes out of your mouth or your nose, it looks just like an impact spatter pattern. Who wants to do that experiment? Oh, see, I've got a couple. Good. We're good. Very, very small spatters. Looks just like what we call high velocity impact spatter. Spatter produced by ammunition. Do you think there's something about spatter that comes out of your mouth or your nose that may distinguish it from spatter? Other just regular impact? Go ahead. Pardon me? Snot, absolutely. Sometimes you see in these spatter patterns the trails of snot with the blood. And you go, yeah, that looks a little bit more like an expirated pattern. Swipes. This is kind of cool. It's like the artistic part of bloodstain pattern analysis. If I have blood on my hand, I now walk over here and I do this. If that blood is still liquid, I now deposit that blood on the wall. Sometimes I can tell which way my hand was moving by the direction of that swipe. So, do you think the swiping medium here was going from left to right or right to left? And why do we think left to right? Just feel it, don't you? A little bit more feathery on this side. A little less on this side, a little bit more on this side. You're absolutely right. That's a swipe pattern. But that tells us something, right? That tells us somebody was moving in a particular direction, or their hand or their fist was moving in that particular direction. So we've learned a lot right now, and I want you to actually apply it. But before we do that, just to the next one. Oh, we've got to show the swipe, of course. It's not nearly as good as something coming out of somebody's mouth, really. So now they have blood on a tissue, and they're moving it against a piece of plexiglass. And you can see the swipe pattern that's produced. More at the beginning, less and less as it goes along. And this is a really interesting part. Sometimes it's not as feathered at the end, but you get these, what I call snow dumps. Well, we're all Canadian, we can think about this. Think about a snow plow, and they're plowing the snow, and then the plow goes up a bit, and there's a little bit of snow left there, right? That's what's happening here. You have something with blood on it, moving along, and then coming up, dumping some of the blood. Sometimes there's so much blood that gravity takes over. Gravity's there all the time. And it causes what are called flow patterns, okay? So this is just blood under the force of gravity. So let's have a look. So this guy, instead of coming out of his mouth, is coming out of his nose now. But ignore what's coming out of his nose, okay? Look at this. That's a flow pattern. So was he upright or lying down when that flow pattern was made? Upright. about this. Think about stage scenes, such as suicide scenes. Not suicide or not, where you have somebody that's lying down in a bed with the gun, hole in the head, but with a flow pattern going this way. First thing you think, that's a stage scene. Because you can't be in bed like this and shooting yourself and having the gravity work in that horizontal way. It has to be vertical. It has to be toward the center of the world. So that's what we'll look for at autopsies, on photographs. We look for the flow patterns, because every time we see a flow pattern, we know where people were situated at a particular time in relation to the center of the world.